Today, I will be discussing with you two important topics. One topic will be relating to achieving very low temperatures. What sort of cryogenic systems one has to use for achieving very low temperatures? This is the topic, first topic what we will discuss. And the next topic will be the different cryogenic fluids and their properties. Okay. So I hope I can cover it in 2 hours. If it is not possible, we will anyway have the next class. We'll add some more information, what we have left out in this class. Okay. Okay. Let us, what is the plan of my talk? First of all, I would like to introduce you to very low temperatures. Okay. What do you mean by very low temperatures? We'll try to understand. And then there are some systems which can be used for achieving these low temperatures. One is adiabatic demagnetization refrigeration system. It is called ADR, adiabatic demagnetization refrigeration. Okay. Now, you can also have what is called the dilution refrigerator system, which is called DRS. Now, we must make measurements of temperature at these very low temperatures, at these very low temperature zones. So what sort of temperature sensors can be used and what is the thermometry at these temperatures that we are going to see and conclude this particular topic. Okay. Now, what is meant by very low temperatures? Let's first understand that. We all know that the temperature in Kelvin is nothing but temperature in centigrade plus 273.15. Okay, so for example, you can see two thermometers which are shown in the slide, and you see the thermometer in Celsius scale, 0 degrees centigrade, 100 degrees centigrade, and 0 degrees centigrade correspond to 273 Kelvin, and then 100 degree corresponds to 373 Kelvin. So this is the centigrade scale. The other one is the Kelvin scale. Now, very low temperature actually corresponds to any temperature below 1 Kelvin. Okay, if you are able to reach temperature below 1 Kelvin, it is called very low temperatures. Okay. Now, on your right side, you see the room temperature of 300 K. You make it 20 times, then you get the sun's surface temperature, which is around approximately 6,000 Kelvin. Okay. And if you decrease this 300 K by almost 60,000 times, then you get a temperature of 5 millikelvin, which is nothing but the temperature which you reach in the adiabatic demagnetization system, or in other words, ADRs. Okay. That sort of temperatures you reach. Okay. Now let us try to understand the various temperature zones. Now 300 K is your room temperature. 273 is 0 degrees Celsius, which is your ice point. Then the coldest temperature on Earth, which is minus 89.2 degrees centigrade in Antarctica at a place called Vostok. The boiling point of liquid nitrogen is 77.4 Kelvin. This boiling point refers to at 1 atmosphere pressure. Please remember that. Boiling point of helium 4, helium isotope 4 is 4.2 Kelvin. You also have the helium 4 isotope will look like this. You have 2 protons, 2 neutrons, etc. Then there are 2 isotopes, helium 4 and helium 3. 2 proton, 2 neutron will be helium 4, and 2 proton, 1 neutron will be helium 3. So the boiling point for this one is 3.2 Kelvin at 1 atmospheric pressure. The temperature of the universe, as per the theoretical calculations, etc., is supposed to be 2.7 Kelvin. If you pump on a liquid helium bath, you please remember we mentioned about the different methods of producing low temperature. One of the method is to have induced evaporation. That means you take a bath of helium and then keep pumping on helium. then you have what is called the, you will have the induced evaporation, and thereby you will lower the temperature of the bath, and it can reach a temperature about 1.2 Kelvin in a metal cryostat, right? Okay. Next, if you pump on the helium-3 bath instead of helium-4, that is, you take the helium-3 bath, then you will reach a temperature about 0.3 Kelvin in such cases. Okay. Now, if you use a commercial refrigerator based on dilution, okay, that is helium-3, helium-4 mixture dilution refrigerator, then you are able to reach about 5 millikelvin. Okay, that is a sort of temperature which you will normally reach. And in the nuclear cooling, using a copper lattice with electrons, you will reach a temperature much lower than this, maybe of the order of something like 0.401 Kelvin. That is the nuclear cooling, what you will achieve. Okay, people are trying to achieve much lower and lower temperature. Okay, and this is something which is a challenging task for people, but you cannot reach absolute zero of temperature, which is the 0 Kelvin. The reason for this is the scale is actually a logarithmic scale, and the logarithmic scale of temperature does not have a zero, and you always end up with, okay, reaching some temperature, but not 0 Kelvin. If you look at the historical development of refrigeration over the years, somewhere around 1880, 70, or around that time, oxygens have been liquefied, and then the nitrogen, and then the hydrogen, and helium in 1908 by Camelingonus. Okay, and then people were able to try to reach further lower temperature, and helium-3 was liquefied somewhere close to 1940s. Okay, and then magnetic refrigeration of electronic magnetic moments were discovered, and they were trying to reach temperatures much lower of the order of something like millikelvin. And then dilution refrigerator came into existence. And then magnetic refrigeration of nuclear moments people tried, and they were able to reach temperatures of the order of, okay, 0.1 millikelvin. And then people are trying to reach ultra low temperatures using the same procedure with the different materials. And people are trying to reach a temperature of microkelvin. Okay. I think the present known temperatures of the order of probably 0.5 or 0.6 sort of microkelvin temperature ranges. Okay. This is the historical development of the situation. Down to 10 millikelvin, the cooling of the gas, cooling of the gas by letting it to do work against a force due to an expansion. The same is the gas employed may be a conventional gas or a helium-3 atoms mixed up with helium-4. And this is your so-called dilution refrigeration system. Below 10 millikelvin, the dominant cooling principle is the demagnetization of nuclear spins of a metal. And we will just see all those details. Okay, let us start with evaporative cooling. If you take your cup of tea, the most energetic tea molecules escape from the cup and they go out as steam. When they actually do this process, they take away their share of heat, and the atoms left behind in the cup are colder because they have lost their energy. So if you do this process much more rapidly, not just to allow it to escape, but to use an external pumping system and try to evaporate this much, much rapidly, then what happens is you lose a lot more energy from the coffee cup, your tea cup, and the tea cup becomes cold. The tea becomes pretty cold. Okay. This is exactly what happens with what is called evaporative cooling or induced evaporation. So, for low temperatures, the working substance what people use is helium, and you have a liquid helium bath, and then you can see a liquid helium cryostat. And what you have is you allow a small quantity of helium to come inside, and then you rapidly pump on it. You will be able to, using a small needle valve, you allow the helium to come inside. And then if you rapidly pump on the helium, you get the temperatures close to 1 Kelvin. So that's why this portion is called the 1K part. Okay. And of course, this is shielded by a vacuum zone. Okay. By a vacuum pumping line is there, a vacuum zone. Okay. Internal vacuum jacket. And the outer vacuum jacket is there with the liquid nitrogen and so on, which is not described here in detail. Right. So by evaporative cooling, what you can do is you can reduce the pressure of on the surface of a liquid. And that means, so effectively what pressure you have is what is called the vapor pressure of the fluid. So the vapor pressure keeps on decreasing. So you can see here the helium-3 and helium-4. Helium-4, see, it has a boiling point about 4.2 Kelvin. And this one has a boiling point about 3.2 Kelvin at 1 atmospheric pressure. As you keep decreasing the surface pressure, okay, and gradually the temperature keeps on dropping. The limitation being that below a particular level, you will not be able to evaporate it further. Okay, so you will reach temperatures of the order of something like, if you have a best evaporating condition, then you will reach temperatures of the order of something like 1.2 Kelvin in the case of helium, around 0.9 to 1 Kelvin in the case of helium-4, and approximately about 0.5 Kelvin in the case of helium-3. Because what is happening, vapor pressure drops down exponentially downwards. Okay, so you will not be able to reach much lower temperatures because the vapor pressure decreases very rapidly. Okay. So what is the procedure to reach temperatures below about 1.5 K? There are two methods. One is called the adiabatic demagnetization refrigerator, which is called ADR. Normally, this can be useful from the temperature range. Useful temperature ranges from 4.2 Kelvin to 70 millikelvin. Okay, please understand 70 millikelvin. That is 70 into 10 to the power minus 3 Kelvin. Right. Now, dilution refrigerator system is another methodology to reach low temperatures. And here you will be able to reach from 1.5 Kelvin to 5 millikelvin. We can even go further down if you are able to use nuclear spins instead of electron spins. We will come back to that a little later. Okay. And right now, let us talk about these two systems. What about the history? Let us look at the history of the adiabatic demagnetization refrigerator system. Cooling to millikelvin temperature by effective electron spins. It was proposed by Debye in 1926 and also by Giach in 1926. The first practical demonstration was done by Giach, McDougall, and Dehaas, Wiersma, Kramer in 1933, and Kurti and Simon did it in 1934. They were able to see that you are able to reduce the temperature, bring the temperature to millikelvin range by their experiments of adiabatic demagnetization. Okay, let us understand what is adiabatic demagnetization. See, if you take a gas in a piston cylinder arrangement, suppose I have a gas in a piston cylinder, and then if I increase the pressure suddenly, then the gas is getting compressed. And what happens is the work of compression is automatically goes into the gas. The temperature of the gas increases, and the temperature becomes T is equal to T plus delta T. That's what happens. Imagine you bring back the temperature of this gas to the original condition. So bring it back to, that means you surround it with an environment where you can bring back to this original state. That is, bring it to the same temperature T, and now suddenly allow the gas to expand. When you expand, pressure drops, the pressure goes down to initial values. So because of this, now the temperature drops for this fluid, for this gas, and temperature goes down T minus delta T. So what happens is, by having a compression, removing the heat, and then suddenly expanding, then the gas temperature can be brought down. So this is by doing the pressure process. Pressure is the variable. You are compressing, okay, exchanging heat with the surrounding, then you are doing expanding, and thereby you are able to reduce the temperature, right? So in the same way, we can think of magnetic energy. So what we will do is, we will imagine a situation, you have a magnetization of the system. Suppose, imagine that you have a lot of magnetic dipoles which are present at a particular temperature T. So what you do is, you apply a magnetic field, so the dipoles are all aligned. So what, because of the process of alignment of the dipoles, the temperature of the system rises, temperature goes from T to T plus delta T. Okay. Now what you do is, you keep this dipoles in conjunction in this magnetic material, and remove this extra heat that has come into picture by having it in a surrounding where the temperature is same as original temperature T. So by the process of decreasing this heat energy, the original the aligned dipole system now reaches the same temperature as initial temperature. Now what you do is, you remove the magnetic field. In this process, the magnetic field is brought back to zero. So the spins are all now misaligned. They go into the opposite, different orientations. By this very process of becoming different orientation, then the temperature of the spins goes down because it is losing a certain amount of magnetic energy, and therefore the temperature drops down. So T becomes T minus delta T. So this process is called the adiabatic demagnetization. So what we have done is, we have, instead of using the pressure, we are using magnetization for reducing the temperature of the spins. So how this is done? You have a 1K pot, about 1.5 Kelvin. Then you have a mechanical heat switch, and then you have a material which has all these magnetic spins, and the spins are all present in the salt, okay, and you have a temperature sensors, etc., arranged to this. Now what you do is, you connect this, now after doing this, first you have magnetize the spins, so the temperature will rise, and then you connect it to the 1K pot by a mechanical heat switch. So the spin temperature will now be brought back to the original value of 1.5 K. Then you suddenly remove this magnetic field. When you remove this magnetic field, the temperature of the spins will go down further, and that you measure, you find it is lower than the original 1K part. So during that process, you disconnect the magnetic switch, the mechanical heat switch, right? But during the adiabatic demagnetization process, right? So this can now be expressed in terms of the entropy change of the salt pill as a function of temperature. So here you can see the entropy is put on the y-axis and the temperature is put on the x-axis. Now, what we are doing is, so this, for example, in two different conditions. First condition is the magnetization to 5 Tesla. That means 50,000 kilogauss, 50,000 Gauss. And then in the other case, 1 Tesla is 10,000 Gauss. So it is 5 Tesla will be 50,000 Gauss. And this is the first case. You magnetize the sample. After magnetizing the sample, okay, by the process of isentropic demagnetization, the point comes to this point, and then you suddenly remove the magnetic field, then the temperature drops, and it drops to a temperature of 70 millikelvin, right? Okay, this is the process of, so magnetization, then isentropic demagnetization, and then the temperature drops to this low value, yeah, 70 millikelvin, right? There are many paramagnetic materials which can be useful for producing this low temperature. Cesium magnesium nitrate, it's called CMN, okay? And the temperature, typical temperature, what you can reach is the range from 10 to 40 millikelvin. And in the range from 40 to 100 millikelvin, you have a couple of salts, chromic potassium alum, cesium chromic alum, and ferric ammonium alum, etc. These are the alums which can be useful in the temperature range from 40 to 100 millikelvin. Manganese ammonium sulfate is greater than 0.3 Kelvin. You can get that. Greater than 1 Kelvin, you can use diprosium gallium garnet, ytterbium OA, and then gadolinium gallium garnet, diprosium aluminum garnet, etc. There are a whole lot of salts which are available, okay, with rare earth materials, and they are useful for temperatures greater than 1 Kelvin. Okay. Okay. Now the adiabatic demagnetization insert is schematic is shown here. I don't know how clear it is, but whatever it is, there are a high vacuum flange, intermediate vacuum flange, and then you have a 4K to 1K zone, and then low temperature experimental stage is there below, and then the refrigerant pill is in this, and this particular portion goes inside a magnetic field. So the magnetic field can be either a horizontal field, or normally it can also be a vertical field. I mean, so that it can be a solenoidal magnetic field can be used in such cases. Okay, a magnetic field solenoid can be used. Now, the magnetic field can be made out of, the magnet can be made out of superconducting materials. So you can have a superconducting magnet in operation along with this, because anyway you have a very low temperature. So superconducting magnet can be useful in this, so can also achieve high magnetic field for the experiments. Right. Now, adiabatic demagnetization refrigerator, for example, the procedures are like this. First, pre-cool the adiabatic demagnetization refrigerator insert in cryostat with the liquid nitrogen, that is up to 77 Kelvin. Then cool the 4.2K, cool the same thing to 4.2K with the liquid helium, okay, and pump down the 1K part, and then to cool the low temperature LTS, the low temperature stage, to 1.5 Kelvin. So you have to bring down the temperature to 1.5 Kelvin. Isothermal magnetization and adiabatic demagnetization of paramagnetic salt will now reach the temperature up to 70 millikelvin. So you can see here the experimental setup. So this is the actual adiabatic demagnetization insert. Okay, this will go into your experimental cryostat. Okay, the magnet insert, everything is there inside. This is a cryostat. Okay, inside the cryostat, this will be inserted, and then the appropriate measurement electronics are all connected to outside, and they will be connected, and you will be able to make monitor the temperature of the salt pill, which reaches 70 millikelvin. Right. I think more details are given here. You can see some pictures of the low temperature stages. So the absorption system with heater, and then 1K plate. 1K plate means it is a temperature reached at this stage is 1 Kelvin, and then 1K pot, where you will have a certain quantity of helium and you will pump on the helium. That's a 1K pot. AC sensitivity sample holder, AC susceptibility coil, sensors, heaters, and then at the lowermost part you have the so-called salt pill, right? So these are the things that are there in the system. Okay, and exploded views are shown here for 1K part, heat switch, all those things are here, right? Some sample measurements are shown here. Since I am not so much familiar with these sample measurements, I will skip it. Maybe we can discuss about it more in detail when case it needed. All that we see is that the temperatures of the different type of materials are shown here. Okay, for different graphs, resistance values, all those things are shown. Okay, oh, sorry. Now let us come to the next type of system, which is the dilution refrigerator system. Okay, so far we have seen the adiabatic demagnetization. Now we'll look at the dilution refrigerator, and let us look at the initial historical status of this. The history says that cooling to millikelvin temperature by a dilution refrigerator was proposed by London, London in 1951. And then later it was also proposed and again supported by the theoretical works by London, Clark, and Mendoza in 1962. But the practical demonstration of this was done by Das and De Bruyn and Taconis in Leiden's laboratory, Leiden's University in 1965. So dilution refrigeration system was actually could see its first experiments in 1965 only compared to adiabatic device. Okay, what does really happen and in a dilution refrigeration system? Now, what happens is if you take helium along with its mixture, suppose mixture of helium isotopes, helium-3 and helium-4, then they actually, depending on the temperature and pressure conditions, you have what is called the phase separations. Okay, suppose we take liquid helium-4, its boiling point is 4.2 Kelvin. You pump on the bath, then you are able to reduce the temperature about to 1.2 Kelvin with the vapor pressure about 1 millibar. Similarly, if you take helium-3 at boiling point is 3.2 Kelvin at normal atmospheric pressure conditions, if you pump on the bath, you are able to reach temperatures of 0.3 Kelvin with the vapor pressure going down to 0.01 millibar. Okay. Now the dilution refrigerator is actually using the mixture of helium-3 and helium-4, and the dilution cooling reaches 0.005 Kelvin or 5 millikelvin. Now you see here the phase diagram, what is shown here, the temperature on the y-axis, and the x-axis shows you the helium concentration. So the normal mixture of helium-3, helium-4 is shown here. This is the blue curve, beyond this blue curve. So, and the temperatures being high, so this is the sort of curve what you normally see. And the superfluid of helium-3, helium-4 is on the left-hand side. That is actually below this, below this blue curve, but the helium-3 concentration being less than somewhere about something like below 75%. Okay. Now, what happens is at a temperature of 0.867 Kelvin, when the concentration of helium-3 is approximately 75% in helium-4, then you come across what is called the phase separation line. In the phase separation line, okay, this you get a two-phase region. In the two-phase region, suppose if you try to have this, a phase separation takes place, and this phase separation is such that if you try to decrease a mix, one liquid with that of the two concentrations together, then what happens is the temperature goes down. Okay, temperature, that is now the phase separation is such that temperature falls below along this line below. Okay, that means if I reduce the helium concentration or if I increase the helium concentration in one of the phase in the mixture, then obviously you are able to see that there is a decrease in, decrease in the temperature. So this is exactly what is being made use of in the so-called helium dilution refrigerator system. Now the working of the dilution refrigerators like this. We start with the helium-3, helium-4 system. So let's assume that we have a helium-4 bath, okay? And then you first reduce it to 1.2 Kelvin bath. Then you pass it through a small constriction, and then you reduce the temperature in a still by rapid evaporation. This is the pump, okay? Vacuum pumping system is shown here. So you are pumping this pumping system, okay? So the pressure here is reduced such that you are able to have a temperature close to 0.6 Kelvin in a still. Okay, the cooled fluid enters a heat exchanger, and then it goes to a concentrated, a mixture vessel, mixing vessel, what you can call it also a mixing chamber. The concentrated mixture of about 85% of helium-3, okay, is now mixed along with a dilute mixture of 6.4% of helium-3. So that is, you have a mixture, you have helium-3, helium-4 mixture. The one concentration is high and the other concentration is low. So when the high concentration one is tried to mix with the low concentration, then automatically cooling occurs. You can see that in the earlier diagram, that is the high concentration is mixed with the low concentration, then the temperature drops down further, goes down. Okay. So that's what happens. And this can be done by using this pumping arrangement. So helium-3 is essentially diluted in a mixture of helium-4. So during the process, the temperature of the bath goes down and you are able to reach lower temperature for this in the mixing chamber. This is exactly what's happened. Okay. So this is elaborated in a slightly better manner in this picture. And you can see here almost now you take the helium-3, helium-4 mixture from 1.5K condenser. You have a main impedance. Then the temperature, it passes through a still at a temperature of 0.7 Kelvin. It has still heat exchanger, then cools down. Then again secondary flow impedance. Then you have again another heat exchanger. And then you have a mixing chamber. In the mixing chamber, the concentrated phase is on the top because its density is lower. And then it mixes into a mixture of 6.6% of helium-3 and 93.5% of helium-4. Okay, if you mix these two together, that is concentrated phase of helium-3 is mixed with the dilute phase of helium-3, then you are able to produce cooling, and that temperature goes down to something like 0.01, 0.005, up to about 5 millikelvin. So now the dilute phase is pumped out by this, by using an external pump. And then again, the gas helium-3 is now pumped out through this one, okay, and through the still, and goes out to the helium pump, and then it is returning back in the steam. So it's a continuous process of producing cooling in the mixing chamber to such that you can reach 5 millikelvin. Okay. Okay, the explanation is given here. The cooling is done by helium atoms, helium-3 atoms from liquid to gas-like phase. To remove the helium atom from the mixing chamber, one needs a still, which is at the temperature of 0.6 to 0.8 Kelvin. From the still, 90% of the outgoing gas is helium-3. And since the vapor pressure of helium-4 is only 5% of that of helium-3. Now, the heat exchangers are inserted between the inflowing and outflowing helium-3 streams to improve the efficiency of this refrigeration process. Okay. Now, the Leiden Cryogenics has given what is called a dilution refrigerator system. So you can see here the dilution refrigerator part, and then the entire electronics, okay, and then the control panel, main relay, the special type of pumps. So special helium-3 pumps are required in this one, and this is your helium-4 container, which is transferring into this system. There are also additional experimental setup for microkelvin. People are also using the microkelvin experimental setup with the dilution refrigerator system. And you can see here the experimental setup. I don't know much about this, so I will just leave it and say only that photograph I will show here. Okay, the dilution refrigerator sits in an outer magnet insert, which is sits in a fiberglass cryostat. The cryostat hangs into the basement on two active vibration isolation pads, which are mounted on the pillars resting in a sand bed. The cryostat is shielded to eliminate the electromagnetic interferences. Okay. In TAFR, they have a dilution refrigerator. The minimum temperature reaches about 5 millikelvin. And all specifications are all given here for the systems which are used, and the various components are identified in the photograph. Okay, 1K pumping tube, feed through, 4K plate, etc., etc. And the mixing chamber is at the bottommost point and so on. Okay, right. Now, we must measure this temperature, whatever that is reached. How do we measure this temperature? Now, for the measurement of temperature, you use a thermometer. So what is a thermometer? A thermometer measures the temperature by using some property, material property, which changes when heated or cooled. So in case of a mercury alcohol thermometer, this we already seen in our other earlier class. And the liquid expands, the volume expansion of the liquid is used as it is heated, and it contracts volume expansion. Because of the same volume expansion, the volume decreases when it is cool. So the length of the liquid column is either longer or shorter depending on the temperature, and then you will be able to measure this, the temperature. Of course, in a digital thermometer, the whatever that temperature element which senses is automatically converted to temperature, and you are able to reach digitally. Now, how do we carry out measurement of temperature at very low temperature zones? What are the thermometers that are available? It's not room temperature, it's low temperature, very low temperature. Now, the temperature sensors which are used at very low temperature is the following. One is low temperature resistance sensors are used. For example, one can use ruthenium oxide sensors from 50 millikelvin to 4.2 Kelvin, and in the magnetic field environment of 9 Tesla. Okay, such is the sort of capability of these ruthenium oxide sensors. You can use this. You can also use carbon composite sensors. This is supplied by Spears carbon resistors. But it is useful from about 10 millikelvin to about 4 Kelvin in a magnetic field environment of 5 Tesla. The response time is very large at low temperatures below 50 Kelvin. It doesn't respond immediately. It responds rather late. So less than 50 millikelvin, the response time is of the order of minutes. Now, there are magnetic susceptibility thermometers which are useful for measurement of temperatures. That means the susceptibility, this we already discussed earlier under thermometer section. Okay, so the susceptibility of the material changes, magnetic susceptibility, depending on the susceptibility, the temperature and on changing the temperature, the susceptibility changes, and they bear a relation like this. The magnetic susceptibility at a temperature T minus the magnetic susceptibility at a standard temperature is equal to C divided by T. So using this relation, one can obtain the magnetic susceptibility values and can be extrapolated to get the temperature. Now, for example, cesium magnesium nitrate paramagnetic salts can be used as the magnetic susceptibility sensor, and the temperature range can be from about 5 millikelvin to 4.2 Kelvin. We can also use squid-based noise thermometer, and squid is superconducting quantum interference device, and noise thermometer based on squid can be useful from about 4.2 Kelvin down to 1 millikelvin, because the noise level varies with the temperature, and directly you can use it for measurement, right? Okay. Now let us try to find out the ruthenium oxide type temperature sensor. And see, temperature is monitored at 1 Kelvin stage, still using ruthenium oxide temperature sensors, and the resistance values, I mean, it saturates below about 50 millikelvin. So for example, there are 2 thermometers which are shown here. The resistance values of ruthenium oxide sensor. Now the temperature on the x-axis and the resistance on the y-axis, that is what is shown here. So you see here, it's a logarithmic relationship, but it gradually keeps on becoming very high at very low temperatures, but it follows a curve, and using this calibration curve, you'll be able to measure the temperature. So as you go to lower and lower temperatures, the resistance keeps on increasing for the ruthenium oxide temperature sensor. Okay, you can do a fitting coefficient with multiple coefficient formula, where multi-dimensional polynomial can be used for fitting, and then you can measure the temperature. In a similar way, you can also use a Spears carbon temperature sensor, and in the Spears carbon temperature sensor, again, you have the fitting done. Okay, the resistance of the thermometer again varies in this manner. X-axis is in temperature scale of millikelvin, and y-axis is the resistance values starting from about very low resistance values to almost 100,000 ohms resistance values. This is for the sphere carbon resistor. The values, the sensors actually saturates the temperatures, the resistance value sort of saturates below about 10 millikelvin, and therefore they are not useful below this temperature. Okay. If you look at, for example, the cesium magnesium nitrate, material, and you can measure the susceptibility of this material with, at different temperatures, you can make a plot of the CMN22. The susceptibility can be plotted as a function of temperature, or rather 1 over temperature is what is plotted here. Then you see follow a straight line curve. So you will be able to use the formula T is equal to constant divided by the magnetization at a particular Tesla T at a particular magnetic field at a particular temperature minus M0. So using this, you will be able to calculate what is the temperature of this one. Okay. Now down to 4 millikelvin, the mixing chamber uses cesium magnesium nitrate mutual inductance thermometer. It is initially calibrated against a sphere resistance sensor. And of course, CMN requires a calibration for every run at 4.2 K. Okay, coming to the last part, which is called the noise thermometry. Okay, squid-based noise thermometry. Okay, this one, it is based on the fundamental Nyquist formula, which shows that the noise is proportional to noise square is proportional to 4 kb, then T into R into delta F. The U square average is the voltage fluctuation that is caused by the thermal agitation of electric charges in an unbiased conductor to a thermodynamic temperature of T. Now you normally have a squid-based thermometer. Now the noise level is continuously monitored. So what is normally done is you measure the reference temperature at liquid helium of 4.2 K, and then you look at the noise spectrum at 4.2 K, and then you measure also the noise spectrum at any other temperature which we are measuring. Using this relations, you will be able to get the temperature value. T is equal to T by T reference is equal to the noise spectrum at a particular temperature T divided by noise spectrum at the reference temperature. So this way we will be able to measure the temperature of this one. So typical noise spectrum is going to be something like this. So you can compare the noise spectrum at one particular temperature with the noise spectrum of another temperature, and thereby you will be able to get what is the temperature of the with respect to the standard one, what is the temperature of the new zone, you will be able to measure, right? So this is all that I have to say. We'll now summarize whatever we have discussed. For example, with liquid helium, you are able to reach a temperature about 4.2 Kelvin, and there are standard thermometers which are available, okay, for measurement of this temperature, like for example, silicon diode, okay, and special type of thermocouples are possible to use up to the temperature of 4.2 Kelvin. If you pump on helium, you are able to reach a temperature close to 1.5 Kelvin, and you also have appropriate thermometers, different thermometers like we have seen sphere carbon resistor, or for example, the ruthenium oxide sensor, etc., can be used for measurements. To reach temperatures of the order of 100 millikelvin or 0.1 Kelvin, we use adiabatic demagnetization refrigeration system or ADRs. Okay, and if you want to go to still lower temperatures, you use dilution refrigerator system, which is called DRS. You go up to about 5 millikelvin. Of course, using nuclear spins, you can still go to lower and lower temperatures. but we are not discussing that part. So I thank you for your listening. So we have discussed about the reaching very low temperatures and the measurement of temperatures at these zones. Okay. So these are things what we have discussed now. So I will stop now. We'll come back in about 10 minutes time to look into the next chapter on cryogenic fluid. Okay. Now the second topic what we are going to discuss today is what is called the cryogenic fluids, different cryogenic fluids, and also discuss about superfluidity. Okay. Now we will be discussing these topics now. Okay, let me make it full screen. Is it full screen now?
Yes, sir. Full screen.
Okay. See, we have studied the cryogenics, different cryogenic fluids, which we come across. The plan of the presentation is going to be like this. We'll talk about we just introduced the subject of cryogenic fluids. Then we talk about nitrogen, oxygen, argon, neon, fluorine, methane, hydrogen, and helium. Now, these are the various cryogenic fluids that we normally come across. Okay, when you come to helium, you have very different behavior of this fluid. Namely, you have a normal fluid and then the superfluid. So the properties of normal and superfluids are very, very different. And similar thing also happens in the case of helium-3, but we don't have any, we will just mention about helium-3. We have already seen the application of helium-3 in reaching very low temperatures. The last lecture, we saw the dilution refrigerator using helium-3. Okay, we conclude this lecture. Let us introduce the topic. We have seen from the beginning various things. We started with the gas state. We are converting to the liquid state. Okay, and we found that you need to consider what is called a critical temperature below which the liquid state of the gas exists. Okay, so until unless you come down below the critical temperature, you cannot produce the liquids of the gas. So then when we came down, we found that there is a need for understanding the phase diagram of substances. What is the behavior of a substance at a given pressure and temperature condition? This is dictated by its phase diagram. We also saw the condensation and boiling points, condensation temperature and boiling points of the cryogenic fluids. The gas to liquid is the liquefaction process. And how do we liquefy? We have discussed at length that various processes. We use Carnot cycle, which is the best efficient process, cycle of operations. But there are practical cycles because we cannot always use Carnot cycle in view of its very high pressure. So we have to use practical cycles. This also we have seen. Then we talked about the gas mixtures, for example, air being a mixture of nitrogen and oxygen, the gas separation and purification process for obtaining pure gas of different sort. So in fact, the gas industry normally deals with the mixture of gases, separates them in using different methods. For example, we have said refrigeration or using adsorption, physical adsorption or chemical adsorption methodologies to purify the gases and then obtain pure gases of the specific component. Okay. Now, all starting point is the air, which is a mixture of various gases. From there, you try to separate the various components. Except in the case of helium, you start with the natural gas sources, and there you obtain helium from the particular natural gas. So these are the things what we have seen already. So now let's start with the nitrogen. Okay, liquid nitrogen is a clear, colorless liquid that resembles water in appearance. Okay, at standard atmospheric pressure is about 103 101.3 kilopascal, and the liquid nitrogen boiling point is 77.36 Kelvin. And if you pump on the liquid, it gradually temperature goes down and it freezes at 63.2 Kelvin. Okay. So liquid nitrogen, you have a gas state, nitrogen gas, you have a liquid state, and then you have a solid state. The gas state is anything beyond 77 Kelvin, and liquid state is between 77.36 and 63.2, and the solid state is below 63.2 Kelvin. Saturated liquid nitrogen has a density of about 807 kilograms per meter cube. In other words, its density is about 0.807, so many grams per cc, or it is lighter than water. Okay, water density is 1000 kg per meter cube or 1 gram per centimeter cube. So compared to nitrogen, this is a lighter fluid. Okay, and the latent heat of vaporization of nitrogen is an order of magnitude smaller than that of water. Okay, I don't exactly have the number here. I think it is here. The latent heat of vaporization is about 199.3 kilojoule per kilogram, whereas that of water vapor is about 2257 kilojoule per kilogram. Nitrogen has an atomic number of 14. It has two stable isotopes with mass number 14 and 15. The relative abundance between the two is 10,000 is to 38. So 14 is actually very large compared to the other component, which is only 38 in number. 10,000 is to 38. They are relatively difficult to separate. Nitrogen exists always as a molecule. Please understand, you always have N2, not N. Okay. Nitrogen is a major constituent of air. Approximately 78.08% of by volume or 75.45% by weight is atmospheric nitrogen. And it is actually you can produce liquid nitrogen by distillation of liquid air. You start with air can be converted to liquid, and liquid air can be distilled. You know, we have seen the distillation process, and in the distillation process, you can separate air into its component and you get liquid nitrogen, right? Okay. Now this video, I don't know whether you have seen it, but anyway, let me try to show it. Incidentally, some videos run very fast. I don't know the reason why it is doing so, but it doesn't matter for us. We only want to look at the things. So we'll see that what about at the appropriate places. Some videos, sound is not important. Sound, I will make sure it is not useful to us. Okay, you see the liquid nitrogen boiling very rapidly out. And then you see the container, glass container, surrounding is fully white. That white is because of the carbon dioxide and water vapor deposition on the surface. Right. Okay, let's go to the next one. Well, incidentally, the nitrogen has enormous applications. Okay, very large number of applications are there for nitrogen. First of all, it's a low temperature fluid. It's an inert fluid. It has a large, application. Large number of applications are there for industrially. And for example, ammonia production, it requires nitrogen. Okay, and also many chemical industries use nitrogen as a fluid, and including for number of applications where you want to reach temperatures down to 63.2 Kelvin, you can use nitrogen, right? So this is the applications of nitrogen. Let's come to oxygen. Liquid oxygen has a characteristic blue color, light blue color. You can see if you look at the liquid oxygen, it has a light blue color, and it is caused by the presence of the polymer, a long chain molecule of oxygen. And at 1 atmospheric pressure, liquid oxygen boils at 90.18 Kelvin. It has a freezing point of 54.4 Kelvin. So obviously, the zone of liquid zone is actually larger in the case of oxygen, from 90.18 Kelvin to 54.4 Kelvin, where it freezes and becomes solid oxygen. Okay. Now, saturated liquid oxygen is heavier than water. The oxygen weighs as 1100 1141 kg per meter cube or 1.141 grams per cc is the density of liquid oxygen at 1 atmospheric pressure and at 15 degrees centigrade. And you see the oxygen is heavier, whereas nitrogen is lighter. Oxygen exists also as a paramagnetic substance. It's a paramagnetic, lightly paramagnetic. And in contrast with many other cryogenic fluids, which is normally non-magnetic. By measuring the magnetic susceptibility, small amounts of oxygen may be detected in the mixtures of other gases. Okay, you find in the mixture of gases, oxygen also is slightly present along with it. Oxygen is very chemically very active. Oxygen generally presents a safety problem in handling because oxygen can support fire. Okay, serious explosions have resulted with the combination of oxygen and hydrocarbon lubricants. Okay, now oxygen has an atomic number of 16 and it has 3 stable isotopes of mass numbers 16, 17 and 18. The relative abundance are 10,000 is to 4 is to 20. So actually the major 16 is a very large major quantity as in the case of nitrogen, which is 14. Again, oxygen is manufactured in large quantities by the distillation of liquid air because it is the most abundant component in the air. And it's approximately 20.8% by volume or 23.2% by weight in the case of oxygen in the air. Now, this video will run fast. Please bear with me. And there is no sound for this. I will try to cut out the sound. Okay. Essentially, it tells you the paramagnetic property of oxygen. So I don't know whether you have seen this video earlier. If you have not seen it, the madam is trying to demonstrate the nitrogen property. When it falls through a magnetic field, there is nothing happens because it's nitrogen is diamagnetic. On the other hand, when you play with the oxygen, you pour the oxygen across the poles of a magnetic field, then you will see what exactly happens. The oxygen sticks in between the two poles of the magnet. The reason being oxygen is paramagnetic, and because it is paramagnetic, it is able to stick between the poles of the magnet. Right. Okay, we'll move to the next one. Okay. Oxygen has again a lot of uses. Please understand. Oxygen is, although it is a safety hazards are there for oxygen, oxygen is useful for welding purposes, breathing. We have all experienced the COVID times where oxygen was badly required for the person to be alive. So oxygen is very much in use in hospitals as well as for breathing purposes, and also useful for oxyacetylene welding purposes. And further, for example, it is serving as an oxidizer in space fuels, okay, along with the liquid hydrogen. And there are various other industrial and chemical applications of oxygen, which I am not going to. You can always figure out what are those applications. Okay. Let us try to discuss about argon. Now, liquid argon is a clear, colorless liquid, and their properties are very similar to those of liquid hydrogen. It is again inert and non-toxic. Okay, so argon is inert and non-toxic. The 1 atmospheric pressure liquid argon boils at 87.3 Kelvin and it freezes at 83.8. That means the liquid range is very, very small in the case of argon. This difference is only about 3.3 Kelvin, right? Now, saturated liquid argon is denser than oxygen since it has argon has a higher molecular weight than that of oxygen. Argon density is about 1,394 kgs per meter cube for saturated liquid argon at 1 atmosphere. Or in other words, it's equal to 1.394 grams per cc. Okay, so you can see here, liquid nitrogen is lighter than water. Liquid oxygen is heavier than water. Argon is still heavier. Argon has 3 stable isotopes The mass numbers are 36, 38, and 40. These are the relative, and they occur in relative abundance in atmosphere. The ratios are 338 is to 63 is to 100,000. So the stable is the maximum isotope maximum content is actually the isotope number 40, and therefore that is the more stable isotopes. Large quantity of it is present. So that is the clear abundant system. Argon is present in the atmospheric air in the concentration approximately about 1% by volume, 0.934% by volume, or 1.25% by weight. That's the content. Because the boiling points of argon is between liquid oxygen and liquid nitrogen, that is slightly closer to liquid oxygen. You have seen the boiling point is about 87.3. Crude grade argon can be obtained by adding a small argon recovery distillation unit. In a conventional distillation unit, you can add a small argon recovery system, and thereby you will be able to recover argon in the distillation of oxygen part, right? Okay. Now let's try to discuss about neon. Neon is another gas that can be produced as a byproduct in an air separation plant. See, these are all inert gases: argon, neon, xenon. All these things are inert gases. Okay. And liquid neon again is a clear colorless liquid, and it boils at 1 atmospheric pressure at 27.09 Kelvin. See, neon boiling point is very low. It is going down, and it has a freezing point of 24.54 Kelvin. Okay. Now the boiling point of neon is somewhat above that of hydrogen, because liquid hydrogen boils at 20.4 Kelvin, whereas neon boils at temperature of 27.09 Kelvin. Neon again is inert, has a large heat of vaporization per unit volume. It has a high density, higher density makes it attractive refrigerant when compared to that of hydrogen. Okay, and neon's atomic weight is 20.183. There are 3 stable isotopes. Okay, the relative abundance is the maximum abundance is, for example, that of 20, because it is 100,000 versus 30 versus 270 something. Okay, relative abundance is maximum for the 20 isotope 20, stable isotope. Okay. Now let's try to consider fluorine. Liquid fluorine is again a light yellow liquid. It has a normal boiling point of 85.24 Kelvin. Okay. And at 53.5 and 1 atmosphere, liquid fluorine freezes into a yellow solid, but upon subcooling further, it transforms to a white solid. Okay. So these are all you have to separate out this fluorine and then try to do all these measurements, etc. Liquid fluorine is one of the most dense cryogenic fluid, and its normal boiling point, it has a density of 1,507 kgs per meter cube, or in other words, 1.507 grams per cc. So it's one of the heaviest fluid. Fluorine is characterized chemically by its extreme activity and indicated by the EMF of the electrochemical cell. The potential is minus 2.85 volts. Fluorine will react with almost all inorganic substances. If fluorine comes in contact with hydrocarbons, it reacts hypergolically with a high heat of reaction, which sometimes sufficiently to so that even the container can be melted and the fluorine can get ignited. So such is the violent reaction of fluorine. So fluorine has to be dealt with very carefully from the safety aspects. Metals as low carbon stainless steel, monal, which are used in fluorine system, develop a protective surface film when brought in contact with fluorine gas. So this surface film prevents further propagation of fluorine metal reaction into the bulk metal. Fluorine is very toxic. The fatal concentration ranges for animals, it is about 200 parts per million in 1 hour time. That is for an exposure time of 1 hour, 200 ppm of fluorine is fatal. For extreme exposure, for an exposure time of, I think it's 15 minutes. It's not clearly written. It is 15 minutes. 800 ppm is fatal. For an exposure time of 4 hours, 50 ppm also is fatal. So fluorine is pretty toxic. So people who are dealing with fluorine in the laboratories, etc., have to be extremely safety conscious for, when you are dealing with such harmful chemicals. The maximum allowable concentration for human exposure usually considered to be 1 ppm per hour in an hour. So, okay, the presence of fluorine in air may be detected by a sharp, pungent odor for concentrations as low as 3 ppm. Okay. Because of its high toxicity, liquid fluorine is not utilized in a large scale. People do not use fluorine in a large scale except as and when required for any specific chemical reaction and so on. Okay, let us discuss about methane. Methane, your natural gas, is the principal component of the natural gas. It is again a clear, colorless liquid. It boils at temperature of 111.7 Kelvin at 1 atmosphere, and it has a freezing point of 88.7 Kelvin. So all these fluids, whatever we have discussed, have a boiling point and then a freezing point. Okay. Now, liquid methane has a density approximately half of that of nitrogen. That is quite light compared to the even nitrogen. So density is about 424.1 kilogram per meter cube or 0.4241 grams per cc. Methane actually forms an explosive mixture with air. And if you range the concentration from about 5.8 to 13% by volume, so you must make sure that there is no air mixing with methane, okay, in these volume ranges. Liquid methane is shipped in large quantities by tankers vessel. The Methane Pioneer made maiden voyage on January 28, 1959, with almost 5,000 meter cube of LNG, or which is called the liquefied natural gas. Since that time, several vessels have been commissioned for LNG transport. You know very well that you can use LNG as a fuel for our transport system. So people are now working in this area for applications relating to transport. Okay. Well, the major component of your natural gas is methane. Okay, that is what you normally know about that. So you can have it as a gas, or you can have it as a compressed gas, okay, CNG, or if you convert it into a liquid, you can have LNG or liquefied natural gas, right? Okay. Now we come to another important cryogenic fluid, which is liquid hydrogen. Now, liquid hydrogen has a normal boiling point of 20.3 Kelvin, or sometimes it's written as 20.4 Kelvin. It has a density at the normal boiling point is very less. It's only 70.79 kg per meter cube, or in other words, it's approximately 0.07 grams per cc. So only this is a very, very small quantity, 70 milligrams, okay, per cc. Now, the density of liquid hydrogen is almost about 114th of that of water. So, liquid hydrogen is one of the lightest of all the liquids. Okay, very light. Hydrogen again is odorless, colorless, and it will that normally will not support combustion, but if in the presence of oxygen or air, hydrogen is quite flammable. Approximately the range from 0 to 5% and 75% and above in atmospheric air is flammable. Experimental research has shown that hydrogen air mixtures are explosive in an unconfined space in the range from about 18 to 59% by volume. Okay, natural hydrogen has two isotopes, and the hydrogen exists always as a molecule. The atomic mass number is 1. And if you have a mass number 2, then it is called deuterium. Atomic mass number 2, 1 proton, 1 neutron system is called the deuterium, whereas 1 proton alone is your hydrogen, right? Hydrogen is actually diatomic. Okay, that means it exists as a molecule. That is, 2 atoms of hydrogen are always present together. Okay, so the single atom of hydrogen is called the nascent hydrogen. So not only it is diatomic molecule, it is made up of molecule like hydrogen, then hydrogen deuterate, and H and HD, they are in the ratios of 3200 to 1. So that means the hydrogen molecules are much larger in number than hydrogen deuteride. The third unstable isotope of hydrogen also exists. It's called tritium, which is H, that is 1 proton and 2 neutron system. That's called tritium. However, it's very rare because it's radioactive. It's radioactive and which has a very short half-life. Okay, so normally people prepare it in radioactive experiments. Okay, for further experiments or analysis and so on, right? So now there are some interesting properties of hydrogen. I think you remember that we had a discussion relating to the gas liquefaction. Under the gas liquefaction, we said there is something called orthohydrogen and parahydrogen. You remember that? Okay, so hydrogen has a orthohydrogen and parahydrogen states are possible in the case of hydrogen, because they exist in 2 different molecular forms. So the properties of hydrogen that sets apart from other substances is the ortho and parahydrogen. We already seen hydrogen exists as a molecule, and the spins of the molecule, the 2 atoms are together, then they have a total spin of 1. So when you have a total spin of 1, it is, you can have 1, 0 and -1 in the case of orthohydrogen. And in the case of parahydrogen, the 2 spins are opposing each other, 1 up and 1 down, and therefore its net spin value is equal to 0. Okay, so the mixture of these 2 forms at high temperature is called the normal hydrogen. It is a mixture of 75% of orthohydrogen and 25% of parahydrogen. So at room temperature, you have 75% of orthohydrogen and 25% of parahydrogen by volume. Now, what happens is when you do a liquefaction process, then the hydrogen actually, there is a composition change from the 75% ortho to 25 plus 25% para to almost 99% of para to plus and a very small percentage of ortho. That's what happens at low temperature. Okay. So you need to take care of this because during the liquefaction process, this conversion does not take place. And we already seen that you need to use specialized catalysts during the liquefaction so that the ortho-para conversion takes place. The equilibrium catalyzed mixture of orthohydrogen and parahydrogen at any given temperature is called equilibrium hydrogen. Okay. That is, if you have an equilibrium mixture, then it's called equilibrium hydrogen. At normal boiling point of hydrogen, 20.3 Kelvin, equilibrium hydrogen has a composition of 0.2% of orthohydrogen and 99.8% of parahydrogen. One could say practically there is entire thing is parahydrogen. That's what you normally say. Okay, the distinction between the 2 forms of hydrogen is the relative spin. Okay, the relative spin of the particles of the molecule of the atoms that make up the hydrogen molecule. And the hydrogen molecule consists of 2 protons and 2 electrons. So the 2 proton each possess a spin, which gives you the total angular momentum of the nucleus. When the spins are in the same direction, the angular momentum of 2 protons are in the same direction. And this is your orthohydrogen. The spin is now 1. Okay. And 1 can exist in a magnetic field. It can be either 1, 0, or -1. So there are 3 possibilities. So this is your orthohydrogen. And when the nucleus spins are in its opposite direction, the angular momentum vectors point in the opposite direction. So the net spin is equal to 0. This is your parahydrogen, right? So now what really happens is when you go to low temperature, the orthohydrogen should get converted to parahydrogen, which normally does not take place in a liquefaction process. So what normally people do is during the liquefaction, you aid the conversion of ortho to para by using additional catalysts in the liquefaction part. Now this we have already discussed at length in the ortho-para conversion because it's an exothermic reaction. It boils off major quantity of liquid what is already produced. Okay. Now let us come to deuterium. Deuterium also exists in ortho-para forms. The nucleus of deuterium consists of 1 proton and 1 neutron, and the high temperature, so that the high temperature composition of the normal deuterium is 2/3 of orthodeuterium and 1/3 of para-deuterium again. Okay. In the case of deuterium, para-deuterium converts to orthodeuterium as the temperature is decreased, in contrast to hydrogen, in which orthohydrogen converts to parahydrogen upon decrease in temperature. So it is exactly the other way. In this case, the parahydrogen gets converted to orthohydrogen as the temperature decrease in the case of deuterium. So now hydrogen deuteride molecule does not have the symmetry that hydrogen or deuterium possesses. Therefore, it exists only in one form. Okay. So hydrogen deuteride, we don't have to worry about it. So we just consider only this orthohydrogen and parahydrogen systems. The deuterium itself is again another combinations. If hydrogen gas temperature is cooled to normal boiling point, the orthohydrogen concentration decreases from 75 to 0.2. This is a conversion. That is, there is a conversion of orthohydrogen to parahydrogen as the temperature decreases. This changeover is not instantaneous, but takes place over a time period. And the change is made by an energy exchange by the molecular and magnetic interaction, molecular magnetic interactions. During the transition, the original orthohydrogen molecule dropped to lower molecular energy level. So thus the changeover involves release of large quantity of energy, which is called the heat of conversion. And this heat of conversion is released, is related to the change in the momentum of the hydrogen nucleus, which changes the direction of the spin. So this energy released in the exothermic by an exothermic reaction, it is greater than the latent heat of vaporization, and therefore liquid hydrogen gets converted to vapor hydrogen. This we already know that. Okay. The 2 forms of hydrogen have different specific heats because of their different weighting of the energy levels in 2 forms. This is shown in figure. I think the specific heat is plotted as a function of temperature. Okay, temperature is expressed in terms of R. I think you have an upper curve which is parahydrogen, and the normal hydrogen and the equilibrium hydrogen is what are all shown here. Am I right? Yeah, correct. Yeah, parahydrogen and then orthohydrogen. I think, sorry, this is the orthohydrogen which is below, and the equilibrium hydrogen has got this curve which is in between. Okay. Because of the difference in specific heats, the other thermal and transport properties are also affected. Parahydrogen has a higher thermal conductivity compared than the orthohydrogen because of the higher specific heats in the system. Right. Now let us come to helium. Helium has two stable isotopes. Either that is called helium-4, which is one of the common stable isotope, and another one is called helium-3. Helium-4 will have, the two neutrons and two protons in its as its nucleus, whereas helium-3 will have two protons and one neutron in its nucleus. Ordinary helium gas contains about 1.3 into 10 to the power minus 4% of helium-3. And when we speak of helium or liquid helium, we normally refer to helium-4 unless otherwise stated, right? Helium-4 has a boiling point of 4.214 Kelvin and density is about 124.8. That is 125 grams per liter of liquid, which is almost about 1/8 than that of the water. It has no freezing point. Okay, helium is a very peculiar liquid. It does not freeze like other liquids, whereas all the other liquids have a boiling point and a freezing point. Helium does not have a freezing point at a pressure of 101.3 kilopascal or 1 atmosphere, but it undergoes a transition from one liquid state to another liquid state, that is a normal liquid to superfluid liquid, superfluid liquid. So at absolute zero, so in fact, liquid helium does not freeze under its own vapor pressure, even if the temperature reduced to absolute zero. At absolute zero, helium-4 must be compressed to a pressure about 25 bar before it freezes as indicated in the figure. Helium-4 is an odorless, colorless liquid and has a index of refraction near the gaseous helium, which is approximately 1.02 for liquid helium. Okay. The heat of vaporization of helium at the normal boiling point is 20.9 kilojoule per kilogram, which is less than 1/100th of water. So you can imagine that water boils, let's say 1 liter, if a certain quantity of heat is able to boil 1 liter of water, almost 100 liters of helium will be boiled with the same heat content. You can see here the phase diagram for helium. Now, this is the solid helium. This is the helium-1, normal helium. Then this is what is called the liquid helium-2. This is the vertical axis, is the pressure axis, and the horizontal axis is the temperature axis. The critical point is somewhere here, which is 5.2 Kelvin. And then as you cool down, you reach the temperature lambda point, which is at 2.17 Kelvin. Okay. Helium is classified as a rare gas. It is very difficult to liquefy. It has unusual properties, have excited much interest that helium has been the object of experimental and theoretical research compared to any of the other cryogenic fluids. We notice from the figure that is shown, the phase diagram of helium-4 differs from other substances. Your solid phase is completely away. So that particular line is far away. So it enters from the one liquid state to another liquid state and in front of the solid gas state. So helium-4 does not freeze under its own vapor pressure. There is no triple point for helium compared to other substances. Helium exists in two liquid phases, liquid helium-1, which is normally called the normal liquid, and liquid helium-2, which is known as superfluid. This happens at a particular temperature, and also the curve looks like a lambda, and therefore the phase transition curve separating the two liquid phases is known as lambda line, and the point at which the lambda point at which the curve intersects, and it occurs at a temperature of 2.174 Kelvin, and the pressure is about approximately 50 millibar. Okay, that's the sort of pressure at which this happens. So this will happen if you start with helium and start pumping on the liquid. Okay. Now, in the figure, you can see the specific heat of helium is plotted, and it looks like the letter lambda, Greek letter lambda, and therefore the transition is called lambda point transition. At the lambda point, the liquid specific heat increases to very high values, and as the temperature decreases through this lambda point, and it was first believed that the transition from helium-1 to helium-2 was a second order transition. However, later work showed that the transition is much more complicated. Because of the specific heat of helium has such a high, large value, and it has a different behavior than compared to the other liquids, the thermal and transport properties of helium also behaves differently. Okay, for example, the thermal conductivity of helium-1 decreases with the decrease in temperature, which is similar to the behavior of the thermal conductivity of a gas. Whereas helium-2 thermal conductivity is enormous, very large thermal conductivity for helium. Heat transfer in any other form of helium-2 is even spectacular when a container of helium-1 is pumped upon to reduce the pressure over the liquid. Liquid initially boils very vigorously, depending on the rate of pumping. And as the pressure of the liquid decreases, pressure on the liquid surface decreases. During the operation, the temperature of the liquid decreases and the pressure decreases, and the liquid gets boiled away. And when it reaches lambda point, then it is absolutely quiet. Okay, the liquid is very clear and there is no bubbles at the surface. Okay, no bubbles are formed, and it's extremely quiet condition, and the uniform temperature is totally uniform throughout the liquid. Okay, it has extremely high thermal conductivity and zero viscosity. Okay, this video again, I will play it such you can have a look at it. I will explain this in a short while. Okay, it will go again rapidly, just don't bother about that. So you can see helium is boiling, and then now it can become a helium-2. It's a very clear colorless liquid. There are a number of interesting properties which the person will display. For example, he will take a porous material. Okay, now normal helium will not flow through this porous material, whereas once it becomes superconducting, superfluid, then liquid helium flows through. It also gives you a property related to the so-called, because of this flow, it gives you a property called film effect. The helium film flow that happens, the helium moves in the form of a film, okay, and goes out and then goes out of the container and against gravity and then falls as drops. Okay, this is called helium film flow. It has extremely high thermal conductivity. So if a heat is applied at any part of the liquid, then the heat transfer takes place. So the liquid rushes through any small opening to make sure that the total liquid is all uniform in temperature, right? So this is what is normally done. Okay, this is called fountain effect. I think I don't remember whether we have discussed this fountain effect, but if needed, we'll discuss it now. Now, the thermal conductivity of helium-2 is very large, so that the liquid bubbles, the vapor bubbles do not have time to form within the body of the liquid. So the heat is quickly conducted to the surface of the liquid. Okay. Helium-1 has a thermal conductivity of approximately 24 milliwatts per meter Kelvin at 3.3 Kelvin, whereas helium-2 can have an apparent thermal conductivity as large as 85 kilowatts per meter Kelvin. 85, where is 24 milliwatts and 85 kilowatts. So this is very large compared to pure copper, even at room temperature. There is some question about defining the thermal conductivity of liquid helium-2, because the thermal conductivity is defined in the ordinary manner depends not only on temperature, but also on the temperature gradient and the size of the container, etc. So helium-2 is having extremely high thermal conductivity. Right. Unusual property of helium is the superfluidity. It also has, it acts as if it has zero viscosity. For explaining the behavior of helium-2, it is proposed that the liquid is imagined to be made up of two different fluids. The people say that helium is consisting of a normal fluid and then a superfluid. In an ordinary fluid, the ordinary fluid and the superfluid, okay, the superfluid has zero viscosity. Okay, they are serving as a mixture of these two. Okay, It has the superfluid has zero entropy and can move fast with the other fluids and the solid boundaries with zero friction. Because of this, using this model, helium-2 can be thought of as a composition of normal fluid and the superfluid. And this superfluid content varies with the temperature. Okay, at absolute zero, the entire composition is 100% superfluid. At the lambda point, the liquid composition is such that 100% it is normal fluid. And as you go below the lambda point, then the superfluid content is formed more and more, and its percentage increases to 100% at the 0 Kelvin. Right. The addition of heat to helium-2 raises the local temperature of the liquid around that point, and the heating is where the heat is added, but which raises the concentration of normal molecules and lowers the concentration of superfluid. The superfluid then moves very quickly and equalizes the superfluid concentration throughout the body. Because of this, superfluid is frictionless, it moves very rapidly, and we therefore see that the apparent thermal conductivity of helium-2 is really due to the fast convection process rather than simply by conduction. Now, another important phenomena is what is called the fountain effect pump, which was observed in helium-2 by Allen and Jones in 1938 and Keller in 1969. And you can see here the if you have a fountain effect, if you see when a heat is so here you just see the picture. In this you have porous materials, okay, porous powder here in this material, and you have an opening, and you are going to apply a small quantity of heat at some zone. When you apply a small quantity of heat, liquid enters through this porous material and jets out as a fountain. When heat is added to the powder in the apparatus shown in figure, the increase in temperature tends to raise the concentration of normal fluid, and superfluid rushes to equalize the concentration. So the superfluid enter into this and to equalize the concentration. Normal fluid, because of its viscosity, cannot leave through the small openings between the fine powder and particles very rapidly. On the other hand, the liquid helium, now quickly builds up. The amount of liquid helium builds up within the liquid as a result of the inflow of superfluid, and finally it spurts out as a fountain at the top of the pipe. And these fountains can have as high as 25 to 30 centimeters have been observed in experiments. Now, they are useful for using in superconducting magnet coolings. So the helium-2 cooled to superconducting magnets can have higher magnetic fields compared to the normal. Now, this is again the film phenomenon, what we discussed in the video, we saw in the video. Another important phenomenon associated with superfluid is roll-in film, which is illustrated here. Suppose I have a liquid helium in a container, and the container is a little away from the main bath. Then the helium can raise over the film, raise over the walls, then drop into the liquid. On the other hand, if this container is inside the liquid, then liquid from the main pool can enter into the container, okay, as a film inside. So the level inside will keep on rising up. In the other case, the level will go down, whereas in this case, the level will go up. If the container is taken out of the main bath, then you will find that the roll-in film forms and the liquid forms droplets, and then they fall into the main pool of liquid. So here, this is all what is explained here. If the beaker is filled with liquid helium-2, a larger container, the beaker is lifted above the surface of helium-2. In the larger container, thin film, approximately about 30 micrometer thick, creeps up the inner wall of the beaker and over the sides, falls back into the liquid in the large container. If the beaker is emptied and placed inside into the liquid of the larger container, then the film again creeps up from the outside of the beaker and then enters into the liquid and fills, and the level becomes identical with that of the liquid in the large container. The velocity of the roll-in this film is called roll-in film, and the velocity of the roll-in film depends upon that film temperature and also these surface conditions over which the film is moving. Okay, so these are some of the things. Another important phenomenon is called second sound, the phenomenon that happens in helium-2. The second sound is similar to the normal sound, but it possesses a definite velocity that it is similar to normal sound, that in that it possesses a definite velocity, which is different from the first or ordinary sound. A standing wave can be set up. The second sound waves can be reflected. Now, the second sound is different from ordinary sound. It is actually the temperature wave, and it consists of temperature waves, and that means the local oscillations of temperature. See, we know normal sound will be pressure waves. It is transmitted, longitudinal pressure waves are transmitted from one end to the other. But on the other hand, second sound in helium is referring to the temperature waves rather than the pressure waves. Second sound was predicted theoretically by Tizza in 1939, about 7 years before it was actually measured by experimentally by Peshkov. The velocity of second sound waves varies from 0 at lambda point and approximately to 239 meters per second at absolute zero. The second sound is a phenomenon relating to the helium-2. Okay, in other words, superfluid helium component, actually. Now let us come to helium-3. Helium-3 is a clear colorless liquid having a normal boiling point of 3.19 Kelvin, and the density is approximately 58.9 kilogram per meter cube. The heat of vaporization of helium-3 at normal boiling point is only 8.49 watts per kg. So small that there is some doubt in the minds of early investigators that helium cannot be liquefied at atmospheric pressure. Similar to helium-4, helium-3 remains in the liquid state under its own vapor pressure all the way down to absolute zero. So we have seen, for example, if you pump on helium, you can reduce the temperature. Helium-3 must be compressed to 2930.3 kilopascal at 0.32 Kelvin, which is the minimum point on the freezing curve as shown in the figure. And before it will solidify, the properties of helium-3 differ considerably from those of the helium-4 at low temperature because of the quantum effects due to the difference in mass, and helium-3 has odd number of particles in its nucleus. Now, helium-3 undergoes a different type of superfluid transition, and that happens at approximately 3.5 millikelvin. So helium-3 also undergoes superfluid transition. We have seen this one already. The mixtures of helium-4 and helium-3 display some peculiar properties. And as you can see here, that helium-3, helium-4 mixture spontaneously separates into two phases. One is the superfluid and richer, one that is superfluid richer in helium-4, and another is a normal fluid richer in helium-3. Okay, so this phase separation phenomena is the basis of dilution refrigerator system. Okay, so you have at let's say 750 millikelvin, about 40% of helium-3 is present. At about 500 millikelvin, okay, you have 90% of helium-3 and 22% of helium-4. And about 0 Kelvin, you have 100% of helium-3 and 6.6% of helium-4. So you can see here, as you move along this curve, when helium-3 gets diluted in helium-4, the temperature drops further down and reduces to lower. So this is the basis for dilution refrigerator. I think more or less we have concluded, seen the different cryogenic fluids. Now I am in many places I have to just read through because it's a matter for only reading. Okay, and there are some we have seen. In conclusion, I would like to say the following: the cryogenic fluids display very, very interesting properties. The subject matter is, so we have some interesting properties. particularly in the case of helium, which shows you the superfluid, and both for the helium-4 and helium-3 display superfluid properties. Okay, and this subject matter is study at low temperature is called condensed matter physics. The studies of helium-3, 4 and helium-3 are still being pursued to obtain more information about this fluid, because understanding the behavior of these fluids itself is an important aspect of the theoretical physics. Okay, superfluidity and superconductivity are baffling concepts, and radical theories are being proposed to understand them, and people have tried to understand this behavior at low temperature. Okay, I think I have more or less covered the cryogenic fluids in this lecture. I think I can now stop my lecture, and I would like to thank you for your patient listening, and hope it was useful to you.